and welcome to the Microchip Is podcast. Join your host, Mike Maynard, as he learns about the technologies, products, and people that make microchip technology what it is today.
Welcome to the Microchip Is podcast. I'm Mike Maynard. Today I'm joined by Tim Morin. Tim is a technical fellow at Microchip who works with the FPGA business unit. Welcome to the podcast, Tim.
Hey, Mike. Thanks for having me.
It's great to have you on. Can we start off by you giving us a little bit of background about yourself and tell us about your role at Microchip?
Okay. Been in the industry for quite a long time. Graduated from college in 85 and had roles at various companies. We're actually 3 companies only. At Microchip, I came with the Microsemi acquisition and I came with the Actel acquisition, and I started off as a product planner. I architected Smart Fusion and Smart Fusion 2. Okay. I moved into a product marketing role. Currently, I run the aerospace and defense marketing organization. I run the product line marketing organization within the FPGA business unit.
And what we're going to talk today is about security for FPGAs. Now, I mean, I'm not quite as experienced as you, but when I first started out as an engineer and FPGAs had, really just come on the scene, security wasn't such a big issue for FPGA design. Why do you think that it wasn't an issue, but now people are really concerned about FPGA security?
So I'm in the same boat you're in. I cut my teeth on an XC3090. Okay. And, security, what's that? Don't need to know. We can blame the internet and the IoT as raising awareness of, cybersecurity threats, okay, across the board. Doesn't matter if it's an FPGA, it's pervasive. And if you want good cybersecurity, you have to have good physical security. You have to have roots of trust somewhere in your system, okay? And, we basically made a root of trust in our FPGAs. So it's really the Internet of Things that spurred more cybersecurity activity and defenses to it. And then, if you really want to have good cybersecurity, you got to have a key somewhere, and you got to store it properly and protect it. That's basically it.
And so, there's very few systems that are not internet connected. So does that mean pretty much all applications really care about security? It's not like the esoteric defense and things like that?
Well, yeah, that's absolutely true. And it's going to become law in the European Union when they pass the Cyber Resiliency Act, okay, which we are actively involved in, right? So every system, whether it's connected or not, should have some kind of a security posture. And good security is always in depth. People like to say defense in depth. You just can't have one lock. It's got to be layered.
That's interesting. You've mentioned 2 things now already. One is the internet. The other is legislation. How have the threats changed over the years? Is it, people are concerned just because of the internet, or are other things happening as well that really matter?
So change is constant. Everybody likes that phrase, right? And the risks are constantly being developed. As a matter of fact, white hat hackers are the good guys. Black hat hackers are the bad guys. And the good guys keep us on our toes because they're always exploring ways to break things, right? And then if you break something, then you know how to fix it. Okay, so there's that kind of activity, and it's ongoing, and it's a favorite amongst universities because people like to do research and, how did this chip work? How can I break it? It's very fascinating, it's engaging, and it's very interesting. The landscape is changing, I think, fundamentally in 2 ways, the threat of quantum computing and artificial intelligence. For quantum computing, I think there's probably an equal number of people out there who think it's going to work. And there's probably an equal number of people that are going to say that it might not work. Okay. But, as it relates to security, it's theorized that it's going to break asymmetric crypto. And asymmetric crypto is primarily used to wrap keys and authenticate systems. And without that, you can't really have any kind of confidentiality in your system. So the safe bet is to plan on it actually working and breaking. And that's exactly what the National Institute of Science and Technology has done by, authoring new methodologies to provide a countermeasure to post-quantum computing. Now, for AI, I think the immediate threat for AI, and I think everybody's seen this, is phishing campaigns, just general email, bogus links and things like that. So just don't click on anything. Now, how that relates to attacking chips is to be determined. I can see it automating things, okay? But AI directly attacking a chip, I'm not sure we're there yet. But it could happen because, I like to keep an open mind. And if you could imagine it, it could happen. That's the way I like to think.
That's not very reassuring, actually, and kind of scary. So, I mean, let's change tack a bit and look at some specific threats and how Microchip mitigates against them. I guess the first thing to start with, I said when I was first an engineer, or we were looking at very early FPGAs, no one cared about security, but actually people did worry a little bit about protecting designs. So when you think about protecting designs, I mean, is that just simply about encrypting the bit stream, or is that more complex?
Depends on your definition of design. From a customer's perspective, an OEM, the design is their system. So they got to protect the whole thing. And we talked a little bit about defense in depth, layered amount of security. So individual components in their systems need to be protected. Okay. And for an FPGA, the majority of FPGAs in the market actually load from an external SPI flash. They're SRAM-based FPGAs. Our FPGAs are non-volatile, and you program them. Okay. And that programming operation or the configuration option for the SRAM-based FPGA needs to be secure. You need to protect the bit stream, because if you can't protect the bit stream, you can't protect the application, you can't protect the system. It's as simple as that. That's the first step.
I guess the other thing that people worry about is trying to do something that impacts the operation of the FPGA. They're sort of trying to tamper with design. So what about anti-tamper? What are people doing with those measures, and how does Microchip avoid or create tamper resistance?
So we invented FPGA security, and we're a large supplier of semiconductors to the aerospace and defense industry. I run the A&D marketing organization, and most of our security requirements come from that market segment. And those are the guys, those are the customers, guys and gals that are completely paranoid about security. You have to assume that a piece of equipment, whatever it is, will be left behind. Okay. And then a nation state will have access to it with infinite resources. Okay. So you really have to have a physical security posture. And in our PolarFire FPGAs, for instance, we have over 30 different types of tamper flags. Okay. And these tamper flags are events to something happening in the system that may not happen. You would know whether it should happen because you created the application, and you can decide, okay, this tamper flag is asserting, I'm not asking the system to do this operation. What should I do? Okay. And so there's 30 different flags that users can choose from to fine tune a potential response to a threat. Okay. And then the responses are pretty simple. You can just lock the IOs out so no information, leaves the chip. You can just reset the chip to prevent the attacker from, accessing information. Or if it's a really securely super critical application, you can zeroize the chip, make it dead. Okay. So we protect our nation's most sensitive equipment, and that's our mindset.
Well, that's really interesting. I mean, you mentioned 30 different anti-tamper flags. I mean, just diving in, are there, really effective ways to protect, for example, looking at power supplies, what's happening on a power supply? Are there things you do to provide even better protection against someone messing with a power supply than maybe some of the competitors can do?
Yeah. So power supply modification, those are typically called glitch attacks, or think of a chip, right? It's made of a whole bunch of transistors, and somebody just lowers the power supply to like a near threshold for a transistor. Then strange things start happening in the chip. You've got a JTAG port hooked up, and you're just interrogating the device to try to get information. We have built in very high speed analog windowed comparators for the three supplies in our PolarFire family that are critical to the device operation. And they're high speed because you want to actually detect an event as quickly as possible. And the other type of attack as it relates to power supplies is glitching attacks, just cycling the power. Okay. And you can't really detect those things with an onboard ADC unless that ADC has a sample rate like in the gigasamples per second, okay, which is practically infeasible, okay? So that's how we protect against invasive, semi-invasive power supply attacks. It's a really simple solution for, a complex problem.
And I mean, that's, clearly challenging to protect against these things. I mean, there's other, questions as well. And I think, one of the concerns, and probably your defense market's going to have a different approach to this than maybe your consumer market, is ensuring parts are genuine. So for most customers, it's just buying from a franchise distributor enough. But then if you look at the defense sector, do they need more?
Yeah, that's correct. I mean, if you buy from an authorized distributor, that's good enough for a lot of people, especially in the commercial market. But for the defense market, they want to know provenance. Okay. And after we're done assembling and testing and packaging a device, we ship it, and we ship it through a distributor. A distributor ships it to, an OEM, and they put it on their board and they start building their systems. At that point, when they put it on the board, they usually program the part with a JTAG port. Well, you can also read out a value from our chip. It's a very long, I think there's like 64 hexadecimal characters that have to be in the right order. And if they're not, that means somebody has tampered with the part during transit. Okay, so it's a very simple check. Say, okay, that's an authentic part. Nobody's tampered with it. And they can also read out a signed digital certificate proving authenticity that this was actually manufactured and tested by Microchip itself. So yes, you're right. Most customers don't want to go through all that activities, but it's a real simple thing to do in manufacturing to just verify that and check that.
You've talked about a lot of these features. You've said they're quite simple, but are they adding costs to the FPGA? I mean, are they taking a lot in the die area?
Nothing's free. I mean, think about your home and, you have a fire. For 20 years, you've been paying insurance and it's like every year I got to cut that check and I hate it and hate it. But when that fire occurs, guess what? You're like, oh my God, it's all worth it, right? That's security. It's kind of a pain and there's a cost, but it's really not that much. If you look at the FPGA, the majority of the FPGA is actually the FPGA part. The system controller, which is what manages all our security and is our root of trust in our FPGAs, can be measured in cents, tens of cents relative to the rest of the part. It's not that much.
Okay, so I mean that's pretty small, but in terms of the design process as well, is it taking time from engineers? I mean, do engineers have to build in, something, for example, to deal with all 30 different potential tamper flags, or can they only use the security they need for the application?
It's up to them. I mean, all those tamper flags are exported to the FPGA fabric as a signal, and you can ignore them. You don't even have to instantiate the tamper macro. If all you want is good, solid bitstream security, it's very easy. It happens automatically in the tool. And the bit streams are, they're side channel resistant. They're resistant to power supply analysis. And it's just easy. It's just like creating a normal bit stream. It's pretty transparent for anybody to secure their bit stream, which is the first step, as we discussed before.
Oh, that's obviously good to hear that it's not going to take a lot of effort. You've obviously, built this track record and this real deep understanding of FPGA security from your defense business. So I'm interested, you've mentioned a couple of things that the defense industry really care about. Are there other things you give examples where defense presents really challenging requirements that Microchip's been able to meet?
Oh, that's a very good question. I would say the defense industry is so far ahead of the commercial industry in terms of what the complete umbrella of what security means. And the phrase we like to use is womb to tomb. Okay. From the birth of the chip, manufacturing, test, assembly, shipping to the customer's design. Okay. Them designing their system, securing it, to them deploying it, and then end of life. And end of life could happen naturally. I'm disposing of equipment, or something falls off of a truck, or a piece of equipment gets left in the battlefield, and you have to have active countermeasures to prevent tampering. That's almost like a silicon supply chain. In parallel, there's activities ongoing about tools. Okay, how do I verify, for instance, that my bit stream actually represents the RTL source? How do I prove that? Okay, And we're working on tools that verify that there are no back doors that have been inserted into the design development process through third-party tools or tools in general. Okay, so they're concerned about that type of security as well. It's really design assurance. Does my chip do exactly what it's supposed to do, nothing more and nothing less? It's a pretty strong security principle. It's also a safety principle as well, right?
I mean, that's interesting. It's amazing how far you've got to go to prove that the FPGA is what it is, does what it should do, and isn't going to get impacted. I mean, you did mention some future threats earlier on when you talked about AI and quantum computing. I mean, how is that going to change the landscape? I know you said it was a little bit uncertain, but are you actually doing something to kind of protect against those future threats already?
So we've actually partnered with a couple of IP partners who provide post-quantum crypto that runs on our FPGA. Okay, so customers can actually deploy post-quantum security applications today. Okay, and as inventors of FPGA security, I think our customers can rest assured that we're going to have countermeasures to future threats.
And that sounds great. And the fact you're already there thinking about quantum computing and you raise the question as to whether it would actually really happen. I mean, it shows that Microchip is definitely taking that, let's go for the more secure approach. I love that.
Yeah, I mean, you cannot bet on quantum computing failing as it relates to security. You have to make the right bet, right?
Absolutely. I mean, Tim, this has been fascinating. We've covered so much. To sum it up, what would you say would be the most important thing for listeners to remember if they're worried about building secure designs using FPGAs?
So there are three principles when building secure designs with FPGAs, and kind of uncannily, the acronym is CIA. So confidentiality, integrity, and then, in the industry, people use authenticity or availability interchangeably, right? Those are the three principles that you have to use in building a system. You can't really add security. It's best to build it in from the ground out. Confidentiality is encryption. Integrity is the data actually hasn't been changed, okay? And authenticity or availability means, I am communicating with the right entity, and I proved all of this stuff cryptographically. Those are the three principles. If you employ them in designing secure systems and then have third parties assess your systems, you'll be good to go.
That sounds great. I mean, before we let you go, Tim, there's one other thing. Do you have like a tip or some engineering advice that, engineers who are listening could actually use to make their FPGA designs a little bit more secure?
I always say, don't be afraid to push buttons. Don't be afraid of failure. Okay. If you don't know anything about security for FPGAs and you think you need to, I mean, come to us. We kind of make it easy for you. I mean, just flat out securing the bit stream and making it side channel resistant, which is a semi-invasive attack, is as simple as pushing a button. It's done for you automatically, and then you can go from there.
That's great. I love that. Really simple, straightforward advice. I mean, you mentioned that if people want, more help, they can come to Microchip. I mean, what's the best place for listeners to go to find more information?
Contact me, tim.morin, tim.morin at microchip.com, and we'll start a dialogue and I'll point you in the right direction.
That's awesome. Tim, this has been fascinating. Thanks so much for explaining why Microchip is secure FPGAs.
Thank you very much, Mike. I enjoyed our conversation. You have yourself a great and secure day.
Thanks for listening to the Microchip Is podcast. Please follow us on your favorite podcast platform to keep learning about the many technologies, products, and people that make Microchip what it is today. Look out for our upcoming Microchip Is podcasts and our new Beyond the Microchip podcast series.